Oye, espérate, ¿tú has visto a José?
¿José? ¿No? ¿Por qué?
Mira, cuando te pongas ese negro prieto lo voy a encender, ¿oíste?
¿Dónde? ¿Dónde estabas tú? ¿Dónde? ¿Dónde? ¿Dónde estabas tú?
Let's try and do this, shall we? This could very well be my last recording ever, or my last words. Isn't that great that you guys can just like be available or like listen to the last pathetic, meager, and measly words of a broken little man. But it's just what it is. What am I gonna say? I mean, and how fitting that my last word should be croaking about optical activity and chirality and stuff like this. I mean, right? And this is it's exactly what I deserve. No matter what, no matter how much I might, point at the darkness and shake my tiny fist. This is probably what I deserve. Anyway, so if this is if this is my final send off, I'm glad I get to spend it with you, you folks. Anyway. Chirality, right? Optical activity. Let's do this. Let's see if I can get through this thing without hawking up too much phlegm on my monitor. On my this is where that spit shield on my microphone really pays for itself right here. So there you go. There you go, spit shield. You're finally doing your job. All right. Optical activity. We ended off there last time, and let me see. Consider the enantiomers of 2-bromobutane. And when we talked about chirality, it is about optical activity for each pure enantiomer. So for our bromobutane here, the optical activity is -23. For S2-bromobutane, it is +23. The plus and minus, of course, refer to dextrorotary and levorotary. That's the directionality that the plane polarized light is rotated in your spectrometer, right? In your optical activity machine, essentially, right? So that determines the chirality of the molecule. That is your measure of chirality there, right? Now remember, S and plus and R and minus have no connection. It's just, R very well could have been plus and S could have been minus. It doesn't really matter. It just doesn't. They don't have a natural connection. The R and S are invented by people, by humans. Plus and minus are Mother Nature herself. All right. So. And as we said about before, there's no relationship between R and S and the configuration the R's configuration and the direction of rotation of light. All right. So should the stereocenter here be designated R or S, right? As long as the bonds are not rearranged, its configuration cannot change. So you can determine if it's R or S at this point here. But the thing about it is that optical activity is not separate or divorced from other experimental conditions. So whenever we take our optical activity, we have to note the temperature, because here, this compound here is levorotary, so minus at 20 degrees. So it rotates the plane polarized light in the negative direction, into the leftish direction, right? While at 100 degrees, it is dextrorotary. So it rotates plane polarized light in the exact opposite position at 100 degrees. So that's something that we need to, keep hold of, right? We don't have, each of these experimental analyses, are not, you have to make sure that you have all the correct, you have to make sure that you note your conditions. If you don't note your conditions, that I wouldn't know, for example, if this amino acid, is plus or minus because of some impurity, or because of some other, or because of some other naturally occurring thing, or because of the temperature. So we have to make sure that we are always very considerate whenever we take down, the optical rotation of these things. All right, all right. So the magnitude and the directionality of optical rotation cannot be predicted. It can only be determined by experimental analysis. So don't think we can sort of predict it. There's only one thing you can predict. If I give you a single enantiomer and I tell you that this single enantiomer is plus 10, right? the only thing you can tell me about the other enantiomer will be minus 10 if it's pure. And you can also tell me, by prediction, if you have equal amounts of both that enantiomer and the new enantiomer that we talked about, they will have an optical rotation of 0, because you will have what is called here as a racemic mixture. They'll be race mates. They'll be race mates, right? And each race mate, if one is S and one is R, and they're identical compounds, they will cancel each other out in terms of their optical activity, because they will have opposite signs in terms of optical rotation, and they will have identical magnitudes. So like one will be 10, one will be plus 10, one will be minus 10, for example. Okay. Predict the optical rotation for a sample of 2-methylbutane. 2-methylbutane, right? Can you predict that sample? Well, not really, right? Because you need to have a lot more information there, right? So don't freak yourselves out by saying, oh, he's going to ask us to predict some optical rotation. You need to have a lot of information before you do that. And here's where we'll talk about that a little bit. All right. So I give you some optical activity, and I give you some values and some molecules and some enantiomers. And what can you tell from there? Well, for unequal amounts of enantiomers, the enantiomeric excess, or EE, percent EE, can be determined from the optical rotation. All right? And so this is where these numbers come into play a little bit. These can tell us about how pure or how much of one enantiomer we have versus the other one if we have an unknown mixture, which is really kind of cool. All right? So let's just say, for instance, we have, this is supposed to be a 9, not 9,2. For some reason, I'm all European today. If the mixture has an optical rotation of plus 9.2, use the formula below to calculate the EE, the percent EE, and the ratio of R to S. All right, let me just see if I can I get the pen on here without screwing up my life? Let me just see. I'm holding the pen the wrong way. How's that one for technology? Select, pointer, pen. Isn't it so fun seeing the old man just sort of dawdle around with computers? 1, 2, 3. This looks to me to be R and S. Okay? So R in this case here is a minus, S in this case here is going to be plus, right? Did I do it right? 1, 2, 3. And so this, you should know, I'm completely sober as I'm recording this thing. I am sober because, well, two things. Well, first off, it's sort of early-ish in the day, but that doesn't stop me. But the other thing is, as you know, I'm pretty sick at this point, and I just don't know that I can hold down my alcohol. So there's your restraint for you. I can make decent decisions for an adult, sort of. So anyway, but I still do have the NyQuil in me, so I'm still going to be a little bit groggy. So there's your R, there's your S, right? I think that's right. Okay. Okay, so this mixture has an optical rotation of 9.2. Use the formula below to calculate the percent EE and the ratio of R to S. Now, we know, without even doing any of the math here, right, we know already what this optical rotation of this is going to be, right? So this guy here, this mixture has an optical rotation of 9.2, plus 9.2, which means that this plus here corresponds to this plus here. All right, and so that means that this optical rotation here, right, corresponds to S here, right? And so now if we have it, so now we sort of ignore this guy here because we now know we only have, we have a 9.2 optical rotation here that's in the plus direction. So what we to do here is, if it has an optical rotation of 9.2, its optical purity is 0.4. How? Because we take the optical purity of that, right, and we say that there here is 9.2 divided by 23.1 is 0.4, or 40% of the mixture here, right? So you have 40% excess. You have a 40%. So in other words, you have a 40% optically pure. So 40% of the mixture consists of an excess of a single enantiomer. So it's not 40% of this mixture is S. You have a 40% excess, all right, of that, right? So that's how much more you have that. That is what is meant by enantiomeric excess. You don't have, even though this is 40%, it's not 40% only. It's 40%, right, in excess of this other enantiomer over there. Okay, so that's how you figure that out. All right, and so there's your simple EE calculation. We'll There's a few more things to that. Maybe we'll talk about that afterwards, but not just yet. Not just yet. Okay. So, stereoisomeric relationships here. We've already seen this before. Just a return to it because we're going to be talking about another facet of this. All right. And so here we are now comfortably in the stereoisomers family of things that we're talking about. And here we have enantiomers, which are, let's just say, non-superimposable mirror images of each other, and diastereomers, which are not superimposable, which are not mirror images. They can be different compounds that are connected in space differently. Okay, so if we look at diastereomers this way, we can say, are cis isomers and trans isomers enantiomers or diastereomers? Well, if you look at this guy here, which is a cis guy here, and this guy here, which is a trans guy here, right? You have two carbons here which dictate, some relationship to these methyls in space. These guys here are pointing on the same side of each other. They're in the same direction of each other. These guys here are opposite of each other, which means if you looked at these as stereocenters, you'd have one stereocenter being one way here and here, and this other guy here would be up like this one here. But if you compare this guy here to this guy here, it would be down. So as you remember from before when we talked about diastereomers, the diastereomer definition that we were playing with was that if you had a molecule that had multiple stereocenters, not all of the stereocenters would be flipped if you had a diastereomer. So diastereomers, when you have multiple stereocenters, not all of those stereocenters would be flipped. Some of them will, but some of them won't. All right. So in this case here, from this cis to this trans, these guys here would be diastereomers because according to the definition that we talked about before, these guys here, one of those carbons would be different in space, and that's indeed what it is. It'd be connected up to the same carbon, but the relationship to that carbon to the other stereocenters in space would be different. So that's why trans and cis isomers are diastereomers. Okay. Here's where it gets a little bit weird. All right, not weird. We've already talked about this, right? But I'm going to show you a really good use for a trick that we've already learned. So draw each of the 4 possible stereoisomers for the following compound, right? And you should also, if you have your models with you, you should make models of each of these things too to convince yourself. Make enantiomeric pairs to make sure that you believe that these guys here cannot be superimposed with each other. Okay, so that's going to be a big thing for you to do. So it's all about you and convincing yourself this is real, not something that I've made up to torture you. Okay. So here's what I suggest that you do. So pair up the isomers in every possible combination and label the pairs as either enantiomers or diastereomers. If you just start off, without having a systematic plan in mind, you're going to get lost, especially if it's more than, especially if this molecule has more than 2 stereocenters. So you want to be super careful about how you lay out this problem, okay? Do that mirror trick thing. It always works, all right? Now, here's what I gave you. All I gave you was this. All I just gave you was this guy over here from the previous slide. Can I go over here? Will it let me do it? Oh, there you go. All I gave you is this, all right? You decide where to start. You decide which diastereomer to start drawing, and so forth and so on. Okay, so I'm going to pick just this one because I'm picking that one. There's no reason. I just pick it just because I feel like it. All right, so I drew that one, and the next thing I draw is my mirror plane. That's the thing that you have to draw next, because that's going to be the thing that's going to help you. That will give you your backbone to be able to solve the problem using this tool. Okay, this is the thing that makes you feel better because you now have a tool that you can use to solve the problem. So remember my thing, because I'm a dude and because I give this advice all the time, think as little as, well, you should think a lot, but think in certain hard problems, like this one here is not an easy problem. In certain hard problems, think when you have to, but turn off your thinking when you don't need to, okay? So, because you don't want to overthink your answer, okay? So the first thing you do is that you take your molecule, you draw it out in a certain type of diastereomer, you draw it, in a certain way, then you draw your mirror plane. Then the thing that you draw its exact mirror image. You draw that enantiomer. You draw this where you have this OH is close to that mirror plane there because this OH is close to that mirror, right? That's how you know how to do. That's how you know to draw a perfect enantiomer every time using my little mirror plane trick. All right. So when you draw your enantiomers, you already have essentially half the problem done, right? So now there's that. But now you have two stereocenters here, and then two stereocenters is gonna give you more work to do. All right. So that's what you want to focus on. All right. Now you go back to your original problem here, and then you say, well, now I've already done the enantiomer. Now I have to switch one of those stereocenters. It doesn't matter which one. I have to switch those stereocenters in such a way to create a diastereomer and put that underneath that original molecule. And that's what I'll do. I will take that guy there, and then this guy here, this OH, because of the way this stereocenter is here, I chose, just because I want to flip that one, I chose to flip this one, right? Just because I chose to. And those relationships there are diastereomers, right? Because these two guys here have, so these guys here are enantiomers because every stereocenter is flipped. That flips to there, that flips to there. This guy here compared to this guy here, there's no mirror plane there, but between here and here, this stereocenter remains the same as this stereocenter here, but this stereocenter here has flipped. So according to our old definition of diastereomers, we've only flipped, we flipped not all of the stereocenters. When you flip all of them, you have enantiomers. If you don't flip all of them, you get diastereomers. And there you go. Now, simply draw the enantiomer of that, and then you go there. And now look at the rest of the relationships to each other, right? So from left to right, if you do this thing my way, you get enantiomers of each other. So this is an enantiomer of that. This is an enantiomer of that. Pardon me. But if you go vertically, you get diastereomers from there to there, and then from there to there. You see how those are easily seen diastereomers. And also, if you go on the diagonal, you'll see that these diastereomers. That these guys here are diastereomers and these guys here are diastereomers. And if you don't believe that, if you don't believe your eyes, the pictures, then simply do your your absolute configuration analysis, and you will see RR to SS. Then you flip one of them here from R to S here, then from SR to RS there. You see how each of these guys here change in the way you'd expect both enantiomers to flip completely and diastereomers to flip partially in terms of their stereogenic centers. Right? Cool? Awesome? See? It's not that horrible. The reason why it's not that horrible, and I hope you believe me, is because you can do this mirror plane trick. You're right every time. Right? And here's also a cool trick too. All you have to do, if you, pardon me. Oh, this might be the big one. All right. Hold on. Let me take a sip of tea here. All right. Okay, I can do this. If you take take any enantiomer, take the RR. All you gotta do, if you assign this correctly, you just have to think once. This is going back to my cat's no thinking policy, right? You have your RR here. If you drew a true enantiomer, if you trust your drawing, then you don't even have to draw. You don't even have to figure this out. You'll know if this is R, this has to be S. If this is R, this has to be S. Go from here to here. You've chosen to leave this stereocenter R right down there, and you've chosen to flip this one. When you flip it from here to here, you only have two choices. If this is R, this has to be S. Done and done. Now you flip both of those to get your enantiomer, and now you have S to R, and then R to S. You see? It's not it all. You have to just think once. Think once on this guy over here. Once you've done that, you're done thinking. You can just draw, right? And everything else will be a lot better for you. Okay. So does it check out also? Well, you can check it out by your absolute configurations, and it also checks out because of our 2 to the n minus meso stereoisomer calculation, right? So you do your 2 to the n minus meso total stereoisomers, where n is the number of possible stereocenters. So here you have 1, 2, 2 to the 2, 2 to the 2 minus 0 gives you 4 total stereoisomers. Yep, you are golden. So you have 4 stereoisomers total. All right. See? Not too bad. All right, so total stereoisomers here, like look at something that is as ubiquitous as cholesterol. All right, the thing that is pulsing through my veins and my yeah my bloodstream right now. Just look at these numbers of stereocenters and look at what's the maximum number of possible cholesterol. Yeah, cholesterol. Woof! How's your NyQuil? So what is the maximum number of isomers for cholesterol that you can have here? Just do 2 to the n, right? Where's your n here? 1, 2, 3, 4, 5, 6, 7, 8. 2 to the 8. Holy crap. Right? Crazy. All right. Symmetry and chirality. So the thing about meso, we haven't really officially talked about this thing yet in lecture, really. Any compound with only one stereocenter will be chiral and have optical rotation because it's because that's just how things are. However, compounds with even numbers of stereocenters may or may not be chiral depending on what it is. Right? This trans 1,2-dimethylcyclohexane has a certain, believe it or not, these two guys here, this guy here and this guy here, have a certain stereochemistry. And you might easily be able to draw the enantiomer of this. If you draw your dotted line right down the middle here, you can draw its enantiomer, and this trans will be different from the other trans. You will not be able to superimpose both of those guys there, right? You won't be able to superimpose them. All right, and so try it. If you don't, I think you're not going to believe me, so just try it out. All right, so those guys here, you will have 2 stereogenic centers, which will be something that should have something that should have some optical activity. But look at this guy here, this cis guy here. You know that you can't draw a mirror image and have that other one be a non-superposable mirror image, because if both methods are pointing upwards, you know that you can take this guy here, and even with the mirror image, you could fit this right on. You can superimpose this right on top of its mirror image. This is not a chiral thing. And there's an interesting, cute little reason for that too. If you take this molecule as is, and you assign this stereocenter, which will have a certain type of stereochemistry, R or S, this guy here will have the opposite one. And if this guy here is R and has a certain amount of chiral influence to the molecule, this guy here will have the opposite stereocenter, and this will have the equal but opposite influence to the chirality of that molecule. And that's why this guy here will be achiral. So this guy here is chiral, this guy here is achiral. Why? Because if you take this stereocenter here, this will be opposite of that stereocenter. And you can easily figure out these things, sort of, if you know how to look at it. If you take this Haworth projection, which we'll talk about in a second, and you cut it right down the middle and show it a mirror plane right down the center of its molecule. Notice you have an even number of stereogenic centers here. If a molecule has a plane of symmetry, a mesoplane, it will be achiral. It will not have optical rotation. Half of the molecule will reflect the other half, which means R will reflect into S. But it's the same molecule, so this much of R will cancel out this much of S, for example, if that's what we're talking about, right? So half the molecule reflects the other half. Its optical activity will be canceled out. This is the operative term right here, canceled out within the molecule, similar to how a pair of mirror image enantiomers cancel each other out when you have a racemic mixture, right? Think back to a racemic mixture. Why does a racemic mixture cancel each other out? It cancels each other out because one molecule has one amount of R, the other one has the same amount but of S, right? And when you have optical rotation, they will have opposite signs. And so the plus 10 will cancel out the minus 10. And if this side here is going to give you the plus 10 contribution, this guy here will give you the minus 10 contribution. Hence, you will have an achiral molecule, right? But if you don't even want to go that far, just say, listen, you can take this guy here, this cis dimethyl cyclohexane, and you can superpose that onto its mirror image, and that's why it's not a chiral entity. Right? It's achiral, all right? So molecules with even number of stereogenic centers have a plane of symmetry that are called meso compounds. All right, draw the mirror image of the cis isomer and show that it can be superposed on its mirror image. When a compound is identical to its mirror image, it is not chiral, it is achiral. Okay, so determine the relationship between the two compounds below. So is this guy here, can you have multiple stereocenters here? If, you know, multiple stereoisomers here? If so, how much? You know, how many? And the same thing here. Do you have the possibility of having, you know, 2 to the n stereoisomers, 2 to the n minus meso stereoisomers? How about this one here? Do out those, right? And see if you can figure it out. Now, one little thing here that seems to be a little bit tricky to some people. Don't think that this molecule, especially this first one here, is static. It's not frozen in space. You can take this guy here, and you should rotate it around that carbon-carbon bond over there to make it to see if it is meso. Right? And so do whatever you have to do to these things, you know, in terms of bond rotation to get them to look like, you know, just to make it easier to think. So if you say, well, wait a minute, hold on. If I see this methyl here, and there's a methyl here, you know, CH3, right? And over here, there's that carbon, then that carbon. Well, wait a minute, this guy here has a carbon and a carbon also. This guy here looks like it might be symmetrical. Flip it around. Flip this guy here around to make this guy here look like this and to see if all the other stereogenic centers play out. See if you can see if that hydrogen there and this hydrogen here will play. Pardon, I am on a tablet, and the tablet's all cockeyed, and I can't draw straight. Anyway, okay. So that is not. I am just making it worse. But I can't stop because I have the OCD and I can't stop. Okay. All right. So there's that. Okay. So tell me if this guy here is a chiral molecule. Does it rotate plane polarized light? And tell me if this one here also is the same thing. Can this guy here also rotate plane polarized light, or is it achiral? Okay. All right, Fischer projections. This is probably the last biggest, well, sort of, the last biggish thing for this chapter. Well, there's this and there's the epoxidation. Fischer projections were invented by our biology friends for the same reason that Haworth projections were made, right? And the reason why Haworth projections were made is to make things very simple to determine certain stereo centers of very complicated rings. Fischer projections are have the same exact sort of reason for existing. You take a very complicated molecule with several stereo centers in a row, and you can draw them out in a very simple way to be able to, determine certain stereogenic principles of each of the carbons. All right. And so this is just a way to draw these things out. There's nothing really sort of ground shaking about this, but here's what I suggest to you, okay? There's only a few rules to follow here, but there are important rules. The first rule, sort of, I'm going to say is use your model set. Your model set here is going to be your friend here. I really can't stress how important it is going to be for this specific set of problem solving. Why? Because you build a long chain of carbons with several stereocenters on them. And all you got to do, here's all you got to do. All you got to do is look at, draw the, build your models where you have the longest continuous chain of carbon sort of bending away from you, right? So if this guy here was so if we're looking down here, this is going to be my longest chain of carbons here. Here's my carboxylic acid. Here's a carbon here. Here's a carbon here. Here's a methyl here. the carbon chain, the carbon backbone is on the vertical. Have these things hunching away from you like an old man, right? Like an old guy sort of hunching away from you, walking away cursing at you because of maybe you look like his daughter. I have no idea, right? So just hunching away from you, right? And you're looking right down the backbone of that old guy, right? And that old guy's vertebrae is going to be carbon carbon stereogenic centers, right? Like this. Like here you'll have a carbon with a phenyl on this side here and a bromo on this side here. This should feel a little familiar to you because this is sort of like looking down lengthwise of a Newman projection, sort of, right? You're not looking down the barrel of it. You're not doing that. You're looking down, the backbone of it, essentially, right? So let's go back up here. Fischer projections are used to represent molecules with multiple stereocenters. Horizontal lines represent attachments coming out of the page or the screen. All right? Vertical lines represent attachments going back into the page. That means that this vertical line here is actually going to be, for example, here, this carbon, 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 carbon backbone. The longest continuous chain of carbons, it should be drawn in the plane of the paper. But how it's really being perceived, how you should really perceive this thing, is really not, of course, flat, because these two carbons here are not, are not just square flat crosses. These guys here, that central carbon here is curving away from you. The carbon on the left and onto the right they're both sort of coming up, coming out at you, and the ethyl and the OH are both coming at you as well, right? And the methyl here, finally at the bottom here, is curving away. All right. So the thing we have to assume, we have to assume that the longest chain here, the longest carbon chain vertically, is going to be drawn up and down. So vertically. All right. Put the most oxidized carbon up on top. The most oxidized carbon up on top. So if you have a carbonyl, a ketone, an aldehyde, a carboxylic acid, put that at the very top, at the very tippity top. Okay, that's what you want to do. Substituents on the chain are placed on horizontal lines that completely cut across the vertical carbon chain. The best thing for you to do is to build like a 6 carbon chain. On each of those carbons, so on the top carbon, put like a double bond thing to represent like a carbonyl or some sort of carboxylic acid. Around all the carbons going down from it, put like, a red and a blue ball, a white ball, a green ball, put different things on there so you will see what I mean. Make sure that your eyeball is right here, right? Eyeball is right there. And you are looking right down, sort of have the carbon chain sort of hunching away from you like this, right down here. And these guys here, if this is my eyeball right now, right? And I'm looking down here. The phenyl here is going to be on my right side, right? Because coming out, if my eyeball's right here, right? The phenyl here, and my eyeball is in a plane of like this, where this carbon bond is here. The phenyl is going to be to my right, and so will be the OH, will also be to my right. The bromo here will be, of course, to my left, right? The ethyl here will, of course, be to my left. And the carboxylic acid here and the CH3 here are going to be going up and down because that's how it is, all right? And when we draw these things very simply. We just draw these things without the dashes and wedges because that's bond line notation. We want to draw it as a Fischer projection. Fischer projection does not need any of those dashes and wedges because we've already made the assumption that the longest contiguous carbon chain with the most oxidized carbon is going to be vertically on this page. All right? Left and right will be the things that will be coming out at us, sort of coming out like an old vertebrae that's like poking out at us. Okay, I'll see if I can bring in some models on Friday to remind you guys of this. It's not hard at all, and I'll show you how very useful it is. Okay, so bring your mouse sets with you. Okay, especially to discussion. All right, so do these things here, right? Do these Fischer projections, right? See if you can figure it out. These Fischer projections can be used to quickly draw molecules with multiple stereogenic centers, right? And this guy here has 2 stereocenters because there's one here, there's one here. This guy here has 1, 2, 3 stereocenters here. This guy here has 1, 2, 3, 4 stereocenters, right? And this guy here looks just like this guy here, doesn't it? That's because it is. That's how you draw it out. All right. How would these guys here be drawn out if you had to draw them in bond line notation? All right. Let me give you one more thing. Okay. Draw a little molecule right here. Oh crap. Zoop, 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 zoop. There's your CO2H. This guy here is going to be your, I don't know, let's call it a bromo. Let's say this guy here is going to be a fluoro. This guy here is going to be, still going away from you, an isopropyl. I don't know. How about that? How about one of these? I don't know. How about an iodine? There you go, iodine. There's your day in the sun. All right. Oh, hell with it. Let's draw two more carbons. This guy here should be yeah, phenyl. The hell. Why not? Okay. Your task is to, well, draw these guys here out in bond line notation, sort of like this. But take this guy here and convert it into a Fischer projection, okay? Now remember, with a Fischer projection, you just can't look down the side of, down this guy here. You're going to make sure that the carbons are all hunching away from you. Make sure they're all hunching away from you. Make sure that you either flip these guys here down or flip these guys here up, up, up. You can probably flip it, well, I have a tendency to look down on things because I'm imperious, and that's just sort of my personality. Right? But if you take these guys here, here's my eyeball, especially now, it's really crazy, all right? Eyelashes, giant eyebrows. All right. If this is the top of my head, this is where my carboxylic acid is, my most oxidized carbon. That's a good thing. It's already right there. I want to make sure that the carbon backbone is hunching away from me. That's sort of going away from me. That's going away from me. But these guys here are pointing up. These guys here are sort of pointing, like pointing away from me. They're not hunching away from me. So I have to take these carbons here and flip them up. Take this guy here and flip these guys up here. Take this guy here and flip this up over here like so. All right. Leave those, the ion and the fluorine, where they're at. But take the carbon with the phenyl, the carbon with the isopropyl, and the carbon with the bromo on it, and flip them up, and then draw your eyeball with all the carbon backbones sort of hunching away from you, and then draw your things and see what you come up with. Let's do that during discussion, okay? All right. Yeah, there's that. Okay. What's cool about Fischer projections, you can take a Jagunda molecule that has like a cajillion stereocenters and quickly assess if they're an enantiomeric or diastereomeric. By just, doing the old mirror trick. This reflects into that, this reflects into that, they have to be enantiomers, right? Provided, of course, what R's are, right? As long as they're not hydrogens, as long as there's some carbonaceous species, right? And they're different, right? Because these guys here look like, if R1 and R2 are the same, right? They're going to be, one's going to be meso, so careful. All right, so R2, so here, if they're enantiomers, right, just make sure that R1 is not equal to R2, all right? For diastereomers, there's no mirror image, as long as, one of these guys here is this way, the other one here has to just have some stereocenter that's just flipped, right? Just as long as it's not all of them, you can have diastereomers, okay? So there's that. Just make sure that when you look at your meso compounds, if you say, well, listen, I can't, like this methyl here and that methyl here, they don't look, if we're looking at mesos, I can see a meso right down here because it's right down the center of this, these like these two carbons here, right? You can see that sort of, right? We're splitting it in half. You can see how that would reflect into that, but I can't see how this reflects into that. That's because this is a chair representation. It's hard to look at a chair representation and see a lot of symmetry to it. Okay, convert that to a Haworth projection. You'll see very very quickly that it is an achiral meso compound. Right? We can't. I mean, unless you know what to look for, right? And I think we already know what to look for. If you have a ring and you have two identical sets of substituents, and it's essentially a mirror plane between them, right? You can comfortably say that this diastereomer here will be a meso compound, all right? But you can't find a plane of symmetry with the chair conformation of a cis-1,2 dimethylcyclohexane because that's not what this is for. Like this is meant to show you, relative positions of that methyl and that methyl, both with respect, with this guy here being axial and this guy here being equatorial. It's not meant to show you symmetry. This guy here is meant to show you symmetry if you need to see it. All right? So that's why the Hayworth projection, which is, a nice contribution from our biology friends, is a welcomed sort of tool for us to use to really, nail down some symmetry. So some very cool stuff. Okay? So in terms of the theoretical stuff here, so when we want to separate out enantiomers, we would have a hard time doing so because I think you see like enantiomers are only different in terms of like what the receptors would be. Like let's just say like on that molecule that we talked about before, where if you have one molecule that has an R stereocenter, it smells like of orange, for example, and the other one smells of lemon, for example, if it's the other enantiomer. They have different smells to us because they sit in different receptors in our nose, in our body, and that's the result of our own chirality. But besides that, similar sets of enantiomers, other than having different optical activity, will have very, very, very similar or identical, physical characteristics. Similar melting point, similar boiling point, so forth and so on. All right. But because of that, we can't really use like distillation or recrystallization alone to separate out one enantiomer from its partner, from its other enantiomer, or from its antipode. There's a $10 word for you, antipode. It's an old word for an enantiomer. A-N-T-I-P-O-D-E. So if you have a job interview with, and it's like a really old chemist, and you're referring to enantiomer, use antipode. They'll be like, "Hey, Sonny, I haven't heard that since I was knee-high to a grasshopper." And then he'll turn to dust, and then it'll all be a dream, and then you'll be made of Laffy Taffy. I don't know, some hallucinogenic thing. Anyway, so the reason why you can't separate one enantiomer from the other one is because the enantiomers have similar or identical properties with the exception of optical activity. So in that case there, then we would have to have something to help make those enantiomers different compounds to us, right? We have to make them somehow different to be able to act differently, right? And so Louis Pasteur had one way of separating out enantiomers. He performed the first resolution of enantiomers from a racemic mixture of tartaric acid salts. And he just did that by like tweezers, literally tweezers. He took one crystal of one enantiomer and separated out from another one of another enantiomer, and he did that, right? The different enantiomers formed different shaped crystals that were separated by hand using tweezers. That's just how that happened, weirdly. Okay, but it doesn't work for most pairs of enantiomers. This was different because these guys here had multiple stereocenters. But if you have a single stereocenter, you're going to have a big pain in the rear end. All right. So how do we separate out two enantiomers from each other if they just have a single stereocenter? Well, make them diastereomers. How do you do that? You ask, right? You cry. How do you do that? You demand, right? You just take your pair of enantiomers, right? Then take something like look at your enantiomers and hope to whatever you hope to, that you have something that you can latch onto, like an acidic site or a basic site. Here you have a basic site. You have a lone pair right there, right? So those are two basic sites. If I took some chiral acid and threw it in here, then that means if I took this acid here and threw this in, that carboxylic acid or that one here will protonate that guy there and that guy there in different moles. Like so, here you have 2 moles of this, and here you have the equivalent of 2 moles totally of this entire mixture, right? So you have 1 mole of this and 1 mole of this, and then you have 2 moles of this, essentially, right? So here you throw this acid in here, and then this acid here protonates that NH2, and this acid here protonates that NH2 as well. Now, when you do that, you form these 2 ammonium salts. But you don't just make those ammonium salts. You also generate the counter ion of this acid along with it. This goes from an acid to a conjugate base. Ooh, chapter like 1 and 2 material. Holy crap, there he goes again, right? So goes from a base to a conjugate acid, an acid to a conjugate base. What you end up making here is that once this guy here protonates that guy here, you make this ammonium salt here, and this carboxylate salt, after it's given its proton, hangs very close to this NH3+, because that plus attracts that minus. And when you do that, look at this. You have that stereocenter, of course, will hang out with that stereocenter. And similarly, because you have 2 moles of this, when this guy here protonates there, when this guy here protonates that guy here, you'll generate that ammonium chloride salt, and then you'll generate this carboxylate salt. Look at that. This stereocenter from here to here is different. This guy here from here to here is same. You've just generated diastereomeric salts. Diastereomeric salts, diastereomers have different properties. They're different molecules. So they'll have different melting points and boiling points and recrystallization shapes and so forth and so on. So you'll be all set to go, right? And a large amount of my research when I was in graduate school dealt with this kind of stuff, and I can attest to you from the front lines, it works like a charm. All right, so it's a really helpful thing, and people still do it on the research level and also on the production level too. So some of the drugs that you guys take, for whatever ails you, trust me, one of the last steps in the production of any of those pharmaceuticals is some sort of a purity recrystallization process to get the correct enantiomer of the thing that's the most active for you. Okay, so that's a really helpful thing. Okay. So another way to do it too is by taking and we won't talk about this until afterwards, but you take a racemic alcohol, for example, and you throw on something called like a Mosier acid chloride. And don't worry about the chemistry of this yet, but if you have a certain racemic mixture, hook on something chemically to it that has another stereocenter. So you will generate a set of diastereomers. Here and here will be the same stereocenter, but here and here, because this is a 1-to-1 mixture, because this guy here is racemic, right? You will generate that guy there, and they will be separable by by column chromatography or by whatever, or by recrystallization techniques. So again, these two things, so like the thing that we talked about last slide and this guy here, are called resolutions, chiral resolutions, right? Chiral or enantiomeric resolutions. All right. What else? And so here's something else that's coming up, right? So here you have a racemic mixture of this allylic alcohol, and you can make that alcohol versus that alcohol depending on being able to do some chemistry to it. Let's just say this guy here, if you have a set of this racemic alcohol here, and you try and put an epoxide, which is this molecule over here, this stereocenter here will react faster than this guy here, and there's many chemistries that can take advantage of a slow reacting enantiomer versus a fast acting enantiomer. And the reason why they're slow or fast is because the reagents that we use will be amenable to each of those stereocenters. So for example here, if we want to do some epoxidation, some enantioselective epoxidation, enantioselective, what's that word? That means that I want to selectively make one enantiomer. I want to make one enantiomer versus the other one, right? So if I take this guy here, if I take something here, right, and I will be able to form an epoxide from this side of the double bond or the other side of the double bond. So from on top of the double bond here, or on the side or the other side of the double bond, right? And when I do that, I will generate a set, right? A set of enantiomers at that point, right? If you look at them here, they will be enantiomeric, right? And how can I do that? We have lots of chemistry to be able to do that. Most of which is brought on by, if there was ever a guy who was a real life Walter White, it would be this cheerful looking fellow named Barry Sharpless. And Barry, he's a great guy. I think. I don't know. I think he still hates me. He's a great guy. He's at the Scripps Research Institute. If any of you chemists out there who want to do straight up hardcore organic synthesis, this is your guy. He's a fantastic organic synthesis guy. He builds some humongous naturally occurring molecules, which are like trophies essentially. And here's just a partial list of his, his like awards and appointments, right? And what I've always loved about this, what I've loved about this too, is that you have all these like lists of awards and fellowships and honorary doctorates. Honorary doctorates. Like I hear, here, you never came to our college, but we're giving you a PhD from each of these guys there, right? Isn't that fantastic? And these are not like, this is not just, these are from serious places. These are, if you're getting PhDs from Stockholm, yeah, that's a big deal. All right. But what I love about his other awards, sort of like down here, it's where the Nobel Prize hangs out in 2001. It's right about there. If I won the Nobel Prize, I would be wearing a T-shirt and a tie that says Nobel Prize winner all day long. I would have the Nobel Prize prominently displayed in my house. I would take the pictures out of my kids' frames and put a picture of my Nobel Prize in their frames, because I'd be that proud of it. Of course I'm kidding, but I'm just saying it's just like, yeah, no big deal. It's the Swedish prize, Anyway, that guy. He's generated a lot of fantastic science here. And the thing that he's done, one of the big things he's done is that he's generated something called an enantioselective epoxidation, where you take titanium tetraisopropoxide, this guy here, and either plus DET or minus DET. This is diethyl tartrate. This is plus diethyl tartrate. This is minus diethyl tartrate plus terbutyl peroxide. You take this guy here, you take one of those guys here, you take some of that, you throw it in to something that has an allylic alcohol position. So here you have a carbon here, a carbon here, a carbon here. And as long as that carbon that does not have the double bond on it has an OH on it, you can generate a specific enantiomer of epoxide just based on that, right? And we'll come back to this, when we have to, when we have to sort of come back to it, right? But this guy here, if you have your epoxide here, you inscribe your allylic alcohol in a sort of a plane, right? And once you have a plane there, right, just like so here, and then you draw your allylic alcohol. Make sure that your OH is always on the upper right hand quadrant of this plane here, and once you do that, now you're all set to jet. All you gotta do is just say is inscribe it this way, and if you use plus DET, you get this epoxide where the epoxide here is coming up at you here, or if you use a minus DET, the epoxide forms from below the plane. Of this here. The plus DET comes from on top of the plane here. The minus DET comes from below the plane here, right? And then you'll make this epoxide over here, okay? So the good thing about this is that you won't have to know this right now, but you will have to know it at a certain point, and we will come back to this. So to the sharpless asymmetric epoxidation, okay? So plus DET comes from on top, minus DET comes from on the bottom. All you gotta do is write sharpless plus DET or minus DET, and I will take that as enough information for our synthesis. So don't worry about that, all right? And we will go over the catalytic cycle, the sharpless asymmetric epoxidation catalytic cycle when we go over epoxidation, which won't be for a little bit. All right, so don't worry, don't sweat that just yet, okay? But if you want to impress me, or if you want to impress yourself, work these out and see if you can figure it out. Just from what I've given here, you have enough information to already figure it out, okay? For those of you who are doing research and you want to see the original paper, you can look this up here. It's on the Journal of American Chemical Society. It was published in 1980, and these are the page numbers. It's a fantastic little article, okay? But it means so much to chemistry, even current day. All right. So anyway, and we'll come back to this afterwards, okay? So there's your allylic alcohol. Okay, good. All right. So compounds with stereocenters other than carbon, you don't have to worry about too much of this. Some of you have already emailed me about like phosphorus and nitrogen. Don't worry that much about it. Silicon here is in group 3. No, not group 3. Is in 3P. Sorry. and it's right underneath carbon essentially. So this is why you can obviously see silicon as a specific stereogenic center. Germanium, ammonium, and sulfur. The only thing you probably want to maybe look at is like nitrogen here. This guy here, once you have a quaternary a quaternary nitrogen, you can nail down that lone pair that's hanging out over there, and you will lock that nitrogen into this position, right? Because normally nitrogens are a trigonal pyramid, right? You'll see this, right? Wow, that came out pretty rad. I didn't even, well, now I'm gonna, right, R2 for me being as infirm as I am, right? This guy here is not. This guy here can't really be chiral because this lone pair doesn't just stay there. It jumps between here and jumps like on the underside of nitrogen and has these guys here flip on up, and that's something called pyramidal inversion. When this guy here flips on down, and this guy here flips on up, that's called pyramidal inversion. That's why nitrogens have a hard time being chiral as is. But if you lock that lone pair in place with some other R group, then yeah, you can definitely have chirality there, right? Same thing here with sulfur. Sulfur's tricky. Sulfur's tricky. You have to be careful about that. But I wouldn't worry too much about it, except maybe nitrogen if you really want to worry about something. Atrope isomers, chiral molecules that do not possess a stereogenic center. Here, for our last part of this chapter here, this is a binapthal species here. And this binap species, this S binap here and this R binap here are two catalysts that allow us to do some enantioselective reactions, okay? And these guys here do not possess a stereocenter because they all have sp2 hybridized carbons, right? You can't have stereogenic centers if tetrahedral stereocenters unless you have an sp3 hybridized carbon. But here you have only sp2 hybridized carbons, so you can't have those. But why these are chiral molecules is because this is so huge here and here, and this guy here has a hydrogen, this guy here has a hydrogen. These guys here are locked into these relative positions. Like this guy here is always going to be poking up at you. This guy here will always be poking up at you, and this can't ever get around the barrier from there to there. Like this guy here can't ever go behind there. The same thing here with this. You guys, this guy here has a barrier that just can't overcome, right? And there's no way this guy here could ever pivot. This guy here could not pivot around here because of the barrier, because there's too much steric hindrance between like this phosphorus and that phosphorus, and then that hydrogen and then that hydrogen. All right, so you can never have that. But because you have that, you guys, these guys here are locked into a certain into a certain chirality, and these guys here are enantiomers. But any enantiomers, pardon me, any enantiomers that are locked in to chirality because of rotation that is inhibited are called atrope isomers. Atrope isomers. There's your another $3 word for you. Last thing. Last slide, I believe. I hope. I'm going to drop dead soon. Axial chirality. When you have an alene, so you have a chlorine here, a chlorine here. This is an sp2, sp, sp2. If you have an alene, and you should build this molecule, you can take two sets of double bonds, stick them together, and you'll see that chlorine, if you put a chlorine there and a chlorine there, they will have that stereogenic center. You might have two more. Build its enantiomer and convince yourself that you can't superimpose this guy here with this guy here. You cannot. These guys here are true enantiomers. You cannot do it. You say, but you have no sp3 hybridized carbons. How can they be enantiomers? Exactly. These guys here. Imagine this carbon here that just is sort of elongated from a tetrahedral stereocenter. Imagine that's one way to imagine it, right? You say, but you still have a chlorine here and a chlorine here and a hydrogen here and a hydrogen here. You have two of the similar groups. How can they be a stereocenter? This is one of those things where you cannot even though you have no tetrahedral stereocenter, you cannot superimpose this isomer over this isomer, and they're only different. They're only different by each of these substituents positioning in space. That is the only way, you know, that these guys here could have chirality, and that they could be enantiomeric. I get the most arguments from this from most of my students. So please, before you argue with me, and I'm happy to argue with you about it, but you've got to make a model set. And I will be able to sniff. So by the time I get back, even in my half-dead infirm condition, I will be able to sniff out if you are not using your model sets. Because you'll have that look like, do you have your model set? Yeah, that's what you'll say. Like, it's at home, or my fish ate it, or whatever. So whatever, all right? So play with your model sets. They work. Trust me on this one, okay? These are enantiomers because they're not superimposable, and you don't have tetrahedral stereocenters. You have this weird axial thing. This is called axial chirality because the source of chirality is from this central axis of this allene species, this carbon species there, right? It works out. And the reason why is because this carbon, like these two pi bonds here, are in the plane, right here, and these two pi p orbitals here are on opposite sides of the plane. So when you have that, or it should be the other way around. I'm gonna erase it. This guy here is in the plane, and this guy here. Hey, that still sucks. I can't, all right? You know what I'm talking about, right? These guys here are coming out at you. Oh, the OCD. It's coming out at you. Jesus, Joseph, and Mary. These are in the plane. They are overlapping. These guys here are coming out at you and going away from you, of course, right? These guys here are coming up and down, right? All right. And that's the reason why I can have that, because this carbon here actually is the crux of two different planes of these two sets of p orbitals, because of these guys here are, this is an sp hybridized carbon. And you know, when you have sp hybridized carbons, you have two sets of unhybridized p orbitals, right? Go back and look at that part for hybridization if you're clueless for that, all right? Or ask me a question when I am back. I think that's it. God, I hope so. I'm sick of hearing me. Okay, folks, have a good rest of the whatever, and I will talk to you soon. I'm going to die now.